What I have here on the slide is a web page for, at least today, I think Jesus and I are going to coordinate and make it include all of the material that he's going to be talking about. Just want to draw your attention to this, though, because you can get all of the material for what I'm doing. You can just download it from here in case you, I don't know, lose the handouts or something like that. And this is on my web page and has all this stuff on it. Let me begin with the outline here for what I'm going to do. Oh no, wrong thing. What are we doing here? Oh, here it is. So I guess the name that I'm giving to what I'm going to do today is this: Solution Methods for DSGE Models and Applications using Linearization. What we're going to be doing over these 2 days is, Jesus and I together, is we're going to talk about linearization procedures and nonlinear procedures and applications. But my emphasis here is going to be, for the most part, on linear procedures and their applications. So let me give the outline, what I want to do. I have way more here than I could possibly do today. I'm just doing that as insurance to make sure I don't actually, at some point, run out of stuff to say. So, and the last part we may not get to. So what I'm going to do at the very beginning is I'm going to try and put both days into a broad context from a computational point of view. I'm going to talk about the two types of solution strategies that we're going to be focusing on: perturbation methods and projection methods. And I'm going to give an overview. I'm going to do an overview discussion of that. These methods actually go back, well, I guess what seems like a pretty long way. Computation of DSGE models sort of started in the 70s, of approximations to models. Actually, if we go back, now I'm saying it, I realize in the 60s already there was a huge amount of work done. But in the 70s there was a resurgence of this stuff. Then in the 80s, and then a big figure appeared in the 90s. In particular, Ken Judd, who declared that economists were very bad at doing computational stuff, and he proposed these projection and perturbation methods at that time. These things go back to the 90s, and more recently, there's been once again a huge increase in interest in these perturbation and projection methods because there's been an increase in interest in dynamic stochastic general equilibrium models. I think that with the crisis that started in 2008, my impression is that interest in these things is going to explode now, is exploding, that the lesson that a lot of people will learn from and are learning from the 2008 thing is that we have to become much more sophisticated, not less sophisticated than we were before. That is from the point of view of macro, we need to integrate financial factors into our models. And that's going to make things more complicated. Where you see this in particular is if you look at central banks around the world, they're massively beefed up in terms of PhD economists with frontier level skills. So I'm going to start with just describing as an overview in a kind of a simple way, although I'm going to describe the results I'm going to describe are completely general. I'm going to start out by talking about these two basic methods that are used, and then I'm going to work on applications. So the first step I'm going to do is I'm going to go to the simple New Keynesian model, and what I want to do is I want to do a couple of things with that thing. First of all, we're going to derive the nonlinear equilibrium conditions. We're going to need those nonlinear equilibrium conditions for several reasons. One is we may want to use one of the nonlinear methods I've just described above. Another one is that we may want to do optimal policy. In fact, I don't know if we'll get to this later, but there is a a strong view that the right way to represent policy is as optimal policy. In particular, if you look at the Riksbank, for example, you have Lars Svensson, who's a governor there, and they conduct monetary policy in this way. They compute Ramsey optimal policy, and on the basis of what they get from their computations, they construct their graphs and forecasts and make their decisions and so on. So I'm going to use a simple New Keynesian model. One of the things I'm going to do is derive the log linear. I'm going to derive the nonlinear equations and derive this log linear approximation to that thing. I'm going to talk about Ramsey optimal policy, which is going to require that I use the nonlinear equations. We'll see that. And then I'm also going to use this model to talk about Diner, which is, I guess, the computational software for implementing much of the stuff at the very top. The Diner computational software can implement projection methods. It's not perturbation methods. It is not in a position to implement projection methods for reasons that you'll see when in this discussion. So I'm going to use this simple model to also illustrate how to use Diner, and then so we'll be doing that. Actually, does everyone have a laptop with them? Does anybody? I don't see any laptops out there. I see two. I guess there are two people raised their hand. Three. Okay, four. So we'll have to share amongst all of us 4 laptops. And so the idea is I've got a very simple little Diner code. I'll explain how to do Diner. So one of the things I hope that you can get out of this thing is if you don't know how to use Diner, you'll learn how to use Diner. In the process of kind of, playing around with the code to learn Diner, I'm going to convey several substantive principles that are kind of emerged from this modern macro literature. One of them is the idea of the Taylor principle. The other idea is the notion of working capital and how that can destroy the Taylor principle. I'll talk about news shocks, and we'll talk a little bit possibly about monetary policy using the long-term interest rate as opposed to short-term rates, which is very much like the QE2 policy of now. Any event, that's that stuff. Then what I'm going to do is I'm going to get into much more substantive stuff here. Is I'm going to discuss the introduction of financial frictions into dynamic stochastic general equilibrium models, and the big lesson there is going to be there's going to be a new shock that comes out of the analysis. I'm going to take this model, I'm going to take it to the data, and then we're going to come back and we're going to have in our hands a shock. I want to call it a risk shock. As a major driving force for the economy, maybe 50% of fluctuations by one estimate, and we'll discuss that. I had tried to put together a Diner exercise for this thing, however, I did not succeed. This is when you prepare exercises, they have to totally work. They have to be totally bulletproof. And if somebody drops it on the floor, it has to still work on the floor. And this is a rather large modeling exercise. I did not succeed in getting into Diner. And I also failed to take it out of my outline here when I realized I wasn't going to be able to do it. Then the final thing here would be to talk about Ramsey policy, which is to take that discussion and then really put it under a microscope and discuss the various issues, time consistency, something called the timeless perspective, and so on. But I doubt very much that I'll actually get that far. But we'll see. I could if depending on how things go here. So let's begin with the first part. The discussion of perturbation and projection methods for solving DSGE models. These methods do not originate from economists at all. This was actually one of the big messages that Ken Judd made in the 90s when he came along and said, "You guys are totally uneducated. You don't realize that people are solving dynamic models out in other areas." And so he told us about projection and perturbation methods at that time. It was not saying that this was stuff he was bringing to us, but rather stuff that other people found very commonplace. So that's what I'm going to do. So let's talk about the outline of how I'm going to do that. So the perturbation and the projection methods, I'm going to start out by explaining it in a toy model. It has the basic essence of an economic model, but it's a totally simple to allow me in the easiest way to discuss these things. And then what we'll do is we'll go to the neoclassical growth model and talk about projection and perturbation methods in the context of the neoclassical model. That's going to be the simplest economic model I can think of, and we're going to derive some basic properties of what you get from perturbation methods, and we'll discuss some basic ideas with the projection methods. So let's get started with the simple example. So basically, the simple example is the example that you would find if you looked up a book on the implicit function theorem. That's what this is. That's what this is. The whole damn thing is all about. So if let's imagine that we have some kind of a function there, h, which is a function of two variables, x and y, and we imagine that that equation there implicitly defines y as a function of x. So x is some kind of an exogenous variable that's given by some outside mechanism, and then the economic environment has that equation that determines the value for y. And what I'm going to do is I'm going to think about the solution as being a function, this function g here, and so I'm going to be looking for this function g that solves this h of x of y is equal to 0. And we can think of that problem is a problem of solving a functional equation. The thing there at the bottom there, r of x semicolon g, is a function of a function, and I want to find that function that solves the function, the functional equation. And we'll call that r there an error function. That error function is going to be floating around throughout this discussion in this first section here. Okay, first of all, to find such a function, you have to do an approximation. You might say, why do you have to approximate? Why don't you just go get it? And the answer is that finding that function is equivalent to solving an infinite number of equations in an infinite number of unknowns. The unknowns are, for every x, I want to have a y. So that unknown object there, g, is an infinite number of unknowns. And the number of equations is for one equation for each x. So there's a continuum of equations that I'm trying to solve, and with respect to a continuum of unknowns, that's real hard to do. If you have 3 equations in 3 unknowns, that's, I find, very difficult. 4 equations and 4 unknowns is really, really hard. And 5 equations and 5 unknowns, you want to kill yourself. That's so many things. So this is a big deal. And the first thing you have to give up on is the possibility of getting an exact solution. That is to say, finding a g function which sets this functional equation to 0 for all possible x. Now, you can write down special cases where that's easy to do, but in general, in economics, those are very isolated and special things. So the projection and perturbation methods are 2 alternative strategies for approximating that function g. So let me first start talking about the projection methods. And projection methods, another word that we could use for projection methods is that you could call them global methods, as opposed to perturbation methods, which we'll call local methods. Let's talk about the global method, the projection method. So what the projection method says is, okay, let's give up on finding the actual g function. Let's look in a space of parametric functions. I'll call it g hat, and then the parameters of g hat are this vector gamma. It's a finite vector, and what I want to do is I want to choose the gamma so that the behavior of g hat mimics the behavior of the actual solution. So what's the behavior of the actual solution? Well, the actual solution g sets this r of x comma g to 0 everywhere. So why don't we just imitate that, choose the gamma so as to set r hat of x semicolon gamma and make that somehow small a lot. We're not going to be able to make a 0 everywhere, because for that we would need an infinite dimensional gamma, because there's an infinite number of x's. So we're not going to make it 0 everywhere, so we're going to have to somehow make it close to 0 in some thing. So you can see here, by the way, the two major issues that come up with a projection method. Number one, what kind of function are you going to use? And number two, how are you going to define close to 0? In fact, this whole topic of projection methods is actually an enormous one that we will only touch on very, very lightly. And you could write a book about the phrase close to 0, and you could write a book about all the possible parametric functions. So I'm going to now discuss separately the functions and the close to 0 definition. Well, inside the set of functions, there are two types of functions. One of them is called spectral functions, and the other one is called finite element functions or approximations. By the way, the language that I'm using here is taken from, I have a paper with Jonas Fischer in 2000, which there sort of documents where you can find rationalization for the type of language that I'm using here. There's always, as in any field, there's a little bit of differences among different people for what the language is exactly, and there's no exception here. So there's a reference to a paper of mine with Fischer, Jonas Fischer, which summarizes, surveys all of this stuff. And you can find the language there we cite various textbooks to talk about this language. So, because in time series analysis, obviously spectral things have a particular meaning, and this is not related to that. Okay, so spectral functions, that's one type of function as opposed to finite element functions or approximations. So spectral function is a function that has the property that as you move the little gamma guys around, you change the function globally everywhere. So an obvious example of that is a polynomial. If you take a polynomial, a plus b times x plus c times x squared, you change c, you change the behavior of the polynomial all over the place. And so the way you represent these spectral functions, we write it in this form here as a linear combination of a bunch of, well, these things here are called basis functions. And we'll do, I got a little bit confused here whether I wanted a 0 or I wanted a 1. So I put in both a 0 and a 1 here. So what I was thinking about with a polynomial, you like to have a 0 intercept term, and the notation is screwed up here. I suppose this should be a 1 here to be consistent. It doesn't matter, it's all notation. But in any event, the spectral representation can be written, the functions can be written in this form, where this is something called a basis function. And one example of a basis function is where the x's are ordinary polynomials, where this hi of x is actually x to the power I. Now this is a disaster. You never, ever, ever want to use a basis function like this, because the reason is that if you use a polynomial that's of order 3 or 4 or 5, then you got things in this expression here that are something to the power 5, and you have something to the power 1. You get huge imbalances in numbers. It totally screws everything up. So this is only here for the purpose of illustration. It's kind of the obvious thing, but it's certainly an example. In practice, so for example, in actually the first example that I know of where this stuff was applied is in a paper by me and Chari and Kehoe in 1992 in the JPE. Anyway, there we use Chebyshev polynomials, which is very, very carefully crafted. So what you do is the basis function now is t sub I, and t sub I is a so-called Chebyshev polynomial. It's just a polynomial, but it has, the ith guy has power I in there and power I minus 1 and so on in a very particular pattern that's of great interest. And it's rigged up also to be always inside the unit box. So you never get into weird imbalances in magnitude. So you express things as a Chebyshev polynomial by, first of all, mapping your little guy x into the unit box so that you don't do crazy stuff with them. And then that's how you construct this. Thing. Now, I don't want to get into the detail of this thing. I just want to show you just by two examples here of something called a spectral function. And where the parameters are it's these weights. The weights here are the gammas. And so what you do is you choose those gammas so as to make the functional equation as close to zero as possible. What I mean by close to zero, we'll get to that in a moment. Right now I'm talking about the functions. So one class of functions is a spectral functions. Then you also have another kind of function is this finite element function. And the finite element function in some ways is very different from the spectral because the finite element thing, all the parameters, they only influence things in a region, locally. They work hard in this neighborhood and they leave that neighborhood unaffected. With polynomials, you look at the whole polynomial and you jigger around parameters, you change the polynomial everywhere. But with a finite element function, you change some parameters and you're only working on it in one neighborhood. So here's an example of a finite element function. It's piecewise linear. And what the parameters are is the following. The way you construct the parameters is that you create a grid of little xi's. Here's the domain here, at big X. These are all the possible values of x. And then you create a grid, x1, x2, x3, and so on, all the way up to this point. Notice this is not an equally spaced grid that I've got here. You might want to do an equally spaced grid, you might not. Here's a non-equally spaced grid. But part of the definition here of this finite element function, of this piecewise function, is these node points. What are these points here? And then the parameter, gamma, say the fourth parameter, gamma 4, is the height of the function at that node point. And then the function itself is just straight lines in between it. Of course, once you see that, you realize you can do all kinds of stuff because you can make polynomials between the two places, and the polynomials could be they could smoothly merge with a neighborhood polynomial, and so on and so forth. But the point is that about the finite element function is that you can work hard in one region rather than another region. And as you can imagine, that might be helpful in certain circumstances. For example, if you're solving a model with inequality constraints, for example, a zero bound on the interest rate, then what happens is in the neighborhood of where the zero bound starts to bind, the behavior is different. And this offers you a certain kind of flexibility to work hard in this neighborhood and do this stuff in this neighborhood, and do this stuff and do other stuff in another neighborhood, and so on. Whereas the spectral methods is very clumsy in that respect. The spectral method, it's hard to work hard in one neighborhood with your parameters because the parameters influence everything. Of course, you can combine the damn things. You could say it's a spectral thing over here and it's a finite element over here. Get creative with this. There are no, by the way, good theorems here, which is interesting. So it's the creativity of the... Now, fortunately, there is a test for whether you're doing a good job. There is a test for whether you're doing a good job. The test is, did that damn function get close to zero everywhere? Of course, you still have a problem, like, what do you mean by zero? Is 10 to the minus 4 zero? Is 10 minus 8 zero? And so on. But economists know how to deal with that. I'll tell you what zero is. Take the tables in your paper and produce the tables in your paper for some degree of accuracy. Now increase the accuracy and redo the tables. Of course, they're all going to be different. But if the language you use to describe the tables hasn't changed, I say the tables have converged. Now, you have to be very careful because I'm assuming monotone convergence. So they may not change very much, and then all of a sudden, ba-boom, they turn upside down. So you do have to be careful with that. But that's a general principle. There is a fundamental check on whether what you're doing is right, because there's always this error function. And it doesn't matter what you do. If you kill some old person on the street, to get that error function equal to 0, you've succeeded, because that's all you're trying to do. So if you're doing some goofy, crazy thing in terms of space of functions, doesn't matter if you get the error function equal to 0. Now, there's a uniqueness issue, of course, floating around in the background. In general, there won't be just one g function here. You do have to worry about that a little bit. Okay, so this is the finite element thing. This is the two general classes of functions that people work with. And now let me talk about the two general approaches to defining close to 0. So probably the most straightforward thing is called collocation. With collocation, what you do is you, with collocation, you focus in on, I'm using n, little n, to be that letter, denotes how many parameters there are in gamma, how many parameters you put in your function, whatever it is, finite element, spectral, whatever. That's n. And so with collocation, what you do is you pick n, these n, you go and find n points, and then you choose the n parameters to set this thing to 0 everywhere. Of course, in general, you can do that because you got n equations and n unknowns. It's no big deal. But then, and then you also have a nice check available, which is that you can look in between. I guess I don't have. Somehow I thought I would have something to write on a little bit. I want to show you how the picking of these points can be actually quite a tricky business. So I have a hidden file here. It's so hidden, actually you don't have it in your handout, but I'm going to show it to you anyway. This is one of the most fun things I ever saw in numerical analysis. Yeah, so I want to show that to you. I need to unhide them. No, wait, I'm hiding it now. I don't get it. It was already hidden. Unhide. Okay, there. Okay, so now, so this is a problem called I'm being retarded. Wait. No, don't record that last word. Well, why isn't it doing what it's supposed to do? Wait. Go like that. No. Oh, I know. Maybe I know. No, oh no, catastrophe, and I'm about to lose my confidence, and then I won't be able to. Oh, minimize, okay. Yeah, okay, here's the example. Okay, now this is one of the most shocking examples. I took this graph from this thing with Jonas Fisher. This is a problem called interpolation. It's not the same as the problem of solving this functional equation, but it's sort of similar. And the problem is the following. Interpolation is that you have a function, you don't know what it is, but you know its value at a bunch of points, and you're trying to figure out what's going on in between. So see this is a famous example here. It's not due to us. This is a famous example. And what I've graphed here is this thing. The dashed line is this function here. Looks like the nicest function in the world. Who could ever think that any harm could come from this little function? It's 1 over 1 plus k squared going from -5 to going -5 to 5. The interpolation problem is to take the value of the function at a bunch of points. Let's suppose you're capable of doing that. You can't draw the function. Well, here, of course, we see it. But it's a function that you can't draw because you can't evaluate it too many times. You can evaluate it sometimes, and then you want to interpolate in between it. So kind of the obvious natural thing to do is to select a bunch of grid points that are equally spaced. Equally spaced is the natural thing you do. Always go equal space. That's got to be the first thing you would do. And then evaluate the function at those points. So take this point there, and so on. And then draw a polynomial through those points. We even think we have theorems that say that's the right way to go. We don't, actually. In fact, that's the wrong way to go, in fact. But you might think of there's theorems, Bernstein, convergence. No, we don't. This is actually a stupid thing to do. And in this particular example, and you should go home and try this, do it at a party with friends, because they'll be amazed. They'll find you much more interesting. So if you fit the polynomial to this thing, what happens is, as you make these grid points more and more narrow, you would think that the approximating function, which is this one here, you would think that those errors would squish down as you made the grid. But no, the errors become infinitely large. You can actually prove that the errors become infinitely large. They become infinitely large. As you make it finer and finer, you get further and further away on the tails of this function. So equal space stuff ain't the right way to go. It's a terrible way to go. That sequence of approximating polynomials does not converge to this nice little dashed line over here. There are theorems about convergence of polynomials. Go and check those theorems. Those theorems say there exists a sequence of polynomials that converge. This is not the sequence that converges. But if you instead just choose the grid points in a slightly different way, where they are slightly more populated in the tails, there's something called the zeros of a Chebyshev polynomial. Don't worry about what that is right now, but it's a way of getting things getting more populated in the tails. And if you populate them more in the tails at this rate, what happens is you can prove theoretically that you get uniform convergence of the approximating polynomials. So how you choose those grid points, big deal. It's a big deal. Now, of course, if you follow the checking strategy that I am advocating, which is always graph your error function, you would notice this immediately. You don't need to know any theorems or anything. You would notice right away that, hey, the error functions doesn't seem to be getting squished down. You are forcing it to be zero on the grid points all the time. But the more grid points you get here, the worse this error becomes. So the point here, I love this example because it really, numerics matter. How you do your calculations makes a difference. Some level, I guess that must be obvious. If you want a square root, you want to take the square root and not the cube root or something. Okay, so one definition of close to zero is delivered by this idea of collocation. The idea of collocation is you pick a bunch of grid points, a quantity of grid points that's equal to the quantity of parameters in your approximating function, and then you set the functional equation to zero at all of those points. And now, of course, there is a long discussion about this. If you go into my paper with Jonas Fischer, lots of discussion about exactly how to pick those points. Lots of discussion about how it's useful to have points out in the tails, relatively more populated than the tails, and so on. Really by the way, it's all very counterintuitive because in economic applications, having points in the tails tends to mean be equivalent to having points that are relatively low probability. And you kind of, your intuition says, no, I want to get this function to work nicely in the region of high probability. But if you do that, you could in the tails, if you don't choose those grid points right, you could make things deteriorate out there in the tails. Of course, the beauty of all this thing is you don't really have to know all that much, because all you have to do, you can always graph the error function. You always graph the error function. You always have a way of telling whether you're on the right track or not. Anyway, that's collocation. Now, an alternative method is called galerkin, and galerkin takes a very, very large number of points, much bigger than n, thousands of points maybe. And, but of course you can't set it to zero at thousands of points if you only have 10 parameters. So what galerkin does is it takes 10 linear combinations of those points and tries to set them to 0. Like maybe the average, maybe the average is in the tails, maybe the average is in the middle, various types of linear combinations to set those things equal to 0. The weights in that averaging is given by this thing here. So you would have, for each I, for each I, you would have a different weight, and then there's I equals 1 through n, so this here is n equations. You have n equations in n unknowns, and you choose the gamma i's to set those n equations to 0. Of course, how you choose those weights is a huge science. Lots of discussion in the paper with my paper with Jonas Fischer. That's also a huge science. My own guess is you're fine with the damn low collocation thing and not getting all whacked out about this thing here. Although there are some simple strategies for choosing those weights, in fact. Okay, so that's the projection stuff. Let's go on to perturbation. For some reason, before going on to perturbation, I had to say a couple more things about projection. So what the projection does is it works on the global behavior of the function. It's looking at the functional equation over a large range. It's trying to get the error function 0 over a large range when it's looking for its approximate solution. The problem with this procedure is the nonlinear calculations you have to do. You have to solve n equations and n unknowns to do this, and that is one heck of a huge pain, as many of you probably know. It requires tons of babysitting time. You have to sit next to your program. You have to say special magic words so that it doesn't do this or do that. It's a very, very difficult and unpleasant thing to do. And as a consequence, often it is not used today. One reason for that is that in current applications, people are very keen on doing serious econometrics. And the problem is, of course, when you do econometrics, what you're doing is you're changing the model parameters. And each time you change the model parameters, you have to solve the model and compare it to the data. Well, that means solving the model many, many times. And if each time you have to solve the model, you have to solve these nonlinear equations and do babysitting, stay up late at night, sing to your computer program, and all this other stuff, you're never going to get anywhere with that. So this projection methods, while at some level my own intuition would be that those have to be the best method, at the same time, they're often not used. Now, on the other hand, I guess economics is on the one hand this, on the other hand that. You might see a resurgence now of projection methods. The reason is those are uniquely well-suited for dealing with zero bound and the interest rate. The projection methods are well-suited for that. The perturbation methods are silent when it comes to that. Projection methods are obvious ways of dealing with zero bound and the interest rate. In fact, my paper with Jonas Fischer was all about using these methods to solve problems with occasionally binding constraints, which is what a zero bound on the interest rate is. It binds sometimes, doesn't bind at other times. And so my guess is we're going to see a resurgence of projection methods. But nevertheless, they are a huge pain. It requires a capacity for suffering that is much greater than what most people have. I don't know if anybody here, for example, did a dissertation, that does computational stuff. That is suffering. Because programs, they never work. Okay, so anyway, the advantage, as I already just said, is that you can adapt them to to any kind of weird way, because again, because there's so much flexibility when you combine the spectral, especially with the finite element method things. Okay, now perturbation methods are totally local, totally local. They're basically operating off Taylor's theorem, which is one of the most marvelous results in the world. What they tell me is that apparently if they take a little piece of skin off of you and they study the DNA, they can find out what kind of movies you like, what are your favorite hors d'oeuvres, what kind of people you're interested in. All that stuff. And Taylor's theorem is the analog for a function. See, if you take a function that looks like that, then you just study one place in that function, and you can actually learn about what the damn thing is doing all over the place. Under some assumptions, of course. Those are called regularity conditions. As long as the function is smooth enough, you can do that. But, you know, the set of smooth functions, I don't know, I'm not going to state this correctly, but it fits into anything. Well, not discontinuous functions, but certainly non-differentiable type functions. So with the Taylor's theorem, which is kind of what this, and the implicit function theorem, the perturbation method does, is the basic insight that it's using is the fact that functions that, as long as they're smooth enough, can be arbitrarily well approximated by just studying one point. Now, there is a problem, however. As anyone who sits down and gets all excited about this and then starts doing the actual calculations, it could be that if the function's kind of a weird function, that yes, indeed, the Taylor's theorem is true, but you might have to take 149 derivatives at that point, at which point the numerics become unstable and it's really not very interesting. So as a practical matter, when you're doing perturbation methods, you have to hope that 1 or 2 or 3 or 4 derivatives are enough to get you interesting behavior globally. And therein you might be concerned. On the other hand, your only alternative is the projection methods, and those require intense suffering. Some people would prefer to drive a cab for the rest of their lives than ever even touch projection type methods. Okay, so the perturbation methods work on the local stuff. The extreme beauty of the perturbation methods compared to the projection methods is nothing iterative. It's all based on computing eigenvalues and various things. You go, boom, you get the solution. If you want to do estimation, it's very straightforward to do estimation using perturbation methods. Of course, the disadvantages are that you may need enormously high derivatives to get a decent global approximation. And then, of course, if you have important non-differentiabilities, then they don't work. Then they're silent because it has to be. You really have to have the thing being differentiable. And at the moment, there's an extremely important non-differentiability that people are very interested in, which is the binding zero lower bound on the interest rate. So both of these methods have pluses and minuses. But let's get into the perturbation thing. All right. So for the most part, to do the perturbation method, now this is not actually true, but the simplest way of thinking about it is that you need to know the function at one point. Okay, this function g is, I don't know the function, so if I had a method that required that I know what the function was, of course, it wouldn't be a very interesting method. Well, this method doesn't require that you know the function, but it does require that you know the function at a point. And for some economic examples, that kills you. But it turns out, for the mass of macroeconomic examples that are of interest today, that is not a problem. And then what you do is you just use the implicit function theorem to approximate this function g in the neighborhood of that point. And then you use all the regularity conditions that are in the implicit function theorem. There's, things have to be differentiable, number one. And number two, there's certain invertibility conditions that we'll see, I think, in a second in these notes that have to be satisfied. So let's just talk about this just for a minute here. I'm doing this in the toy example because it's the easiest place to do it in. So again, we have this function, when you plug in the policy rule, the correct policy rule g into this function, you get this r of x thing. With a true function, that's equal to 0 for all points in the domain. So, of course, if the r function is equal to 0, well, then its derivative is 0 too. The number 7, you differentiate that, it's 7. It doesn't change. It's always 7. So if the r function is always 7, from that we can derive, or 0, from that we can figure out that that r, the derivative of r with respect to x is 0, the second derivative is 0, the third, the infinite, whatever, derivatives, all the derivatives are equal to 0. And it's on that basis that we're gonna get the, this whole damn thing working. So the way we do this is just differentiate that. Well, let's go step by step. So let's take the first derivative of r with respect to x, but I will need to know the value of the function at this one point. So let's suppose we know the value of the function at that one point. So we're going to evaluate this derivative at x star, and I know what g star is. So I differentiate r with respect to x and evaluate it at x star. So what is that r function? It's this thing. It's this thing here. So the x appears in two places. So here's the first place, and there's the second place, and boom, there's only one unknown here. You see, because I know G star, I'm presumed to know G star, and so G prime is equal to the negative of this thing. And of course, here you can see that, assumption that's required in the implicit function theorem is an invertibility assumption, which is that the derivative of h with respect to its second argument has to be invertible, or in the scalar case, it has to be, non-zero or something. So that's how we get the derivative of this thing. And then we get the second derivative by just doing the same thing all over again. And so now take the second derivative. By the way, if anybody here has tendency towards carpal tunnel syndrome, this thing will give it to you. Because while it's conceptually very easy to do perturbations, it is a nightmare of notation. You can see that a little bit now already with the second derivative. If you go to the third derivative, the fourth derivative, you just want to kill yourself. So it takes a very special accounting type of mind to put this stuff together. Fortunately, all this software now has been put together, so you don't have to get into these kinds of details. But here you get the second derivative, and there's a very important thing that's appearing in here. So if I differentiate this thing twice, the key thing to notice if you look at this expression is that it only has one unknown in it. So you know what G prime is from the first calculation you did. You know what G star is, that's what we're presuming. There's only this one G double prime thing, and it's a linear, solves a linear equation. So this is a recursiveness property, which is you can get you don't have to calculate all the derivatives at the same time. You calculate the first one by doing the first derivative, take the second derivative, and you can build up your derivatives all in that way. Of course, you better hope that things are differentiable and so on, and invertible, and so, for example, if this guy here is 0, then you got a problem. I blotted out, I think you have on your slides a big circle, a circle slide, which gives you an illustration of the implicit function theorem, which I'm not going to talk about. You could look at it, but you can kind of get a feel for what it means, what these invertibility conditions involve, and so on. So you can, by applying this thing sequentially, you can get first G prime, then G double prime, and so on. And now Mr. Taylor steps into the picture with the observation that this G prime of x, under the right condition, is a pretty darn good approximation of whatever function you're interested in, as long as it's got the appropriate over a reasonable interval. As long as you make n large enough, and the thing has all the differentiability properties and so on. So that's the perturbation method. By the way, in the case of the perturbation method, you got the same check. I've never seen this check implemented, I don't think. I'm not sure why. Because you also have this check, because what this is giving you in the end, you're getting a parametric function. The perturbation method applied 2, 3, 4, whatever number of times, or just one time, the linear perturbation, gives you a parametric function, g hat of x. Well, it has a nice feature that the parameters are incredibly easy to compute. They just all pop out of this function, which I know what the function is. I do have to know what G star is, but there's no decisions like, what is my grid going to be, what family of approximating functions I'm going to look at it and stuff like that. There's no real decisions here. Everything goes boom, boom, boom. It's just straightforward calculations. But in the end, what you do have here is a function. And so that function really ought to be plugged back into the original Euler error function to see whether, in fact, that thing is 0 over a reasonable range. Okay, so that's the perturbation and the projection stuff, explained in the simplest way. So now I don't have to explain those things, and I can talk about, I don't have to explain the nuts and bolts of them that I did with my toy example, and I can talk about a couple of substantive results we get from the point of view, well, especially perturbation method, when we're talking about a simple model. So here we have the simple neoclassical growth model. There's no hours worked in here. There is a shock in here. I want a shock because, well, it makes this a little bit interesting. I mean, what I've said up until now, it's not totally obvious what you do when there's uncertainty, so we will extend this in a very simple way, what I just said to the case of uncertainty. So here we have our little example. I'm also writing everything, little k is the log of the capital stock. So I'm expressing, this is the production technology here. I'm expressing it in terms of the log of the capital stock, little k. Big K is the actual capital stock. Here you can see, here's big KT, and so you have to exponentiate my little guy in order to do that. The reason for doing that is what later on we're going to get from these methods, in particular the perturbation method, we're going to get parameters, coefficients, and they're going to be on things called k. If k is the log of the capital stock, then it's easier to interpret than if k is the actual capital stock, because the units are not well pinned down with actual quantities like that. Okay, so let's look at the analog of that little h function that we're trying to set to 0. That analog is this efficiency condition, the first order condition associated with the investment decision. So here you see consumption today, and notice I have to exponentiate this little k, because this is supposed to be the actual capital stock here. So I have to exponentiate that, and so here's our, this is going to be the analog of our guy here, of our error function. I'm imagining that at time t, these we're sitting at some time t, so kt and at are given numbers. Implicitly, therefore, epsilon t is just a given number. It's hiding inside a, of course. But there is one source of uncertainty here, which is the epsilon t plus 1. At any point in time, that's kind of the situation. And for purpose of the discussion, it's convenient to think of that neoclassical model as really a sequence of models indexed by this parameter sigma. So the variance of epsilon t is sigma is, oh, I don't like that notation. Sorry, this is, the variance of epsilon t plus 1 is actually v sub epsilon. And what I'm going to do is I'm going to put in sigmas in front of the epsilons and drive them potentially to 0. So sigma equal to 1 is the model, is the actual model, and then I have a sequence of models as sigma goes to 0. Screwed up on the notation. I just noticed that now a little bit. But this thing is that this sigma here, when it's equal to 1, it's equal to the model that I'm interested in, and when sigma it goes down towards 0, it goes to a version of the model where there's no variance. In the subsequent slides, this is going to be the notation will be more sensible. So here you have I put the sigma in front of here. So what I'm going to look for is I'm going to look for a solution to the model. Now, kind of as you all know, there's two ways of thinking about solutions to dynamic models in economics. One is the sequence perspective. So you think of a solution as a sequence of numbers. When there's uncertainty, it's a sequence. You think about an event tree. The sequence of numbers is really the numbers that fill out a tree with lots of branches, as opposed to when it's deterministic, a sequence of numbers is just a sequence of values of the capital stock. So one way of thinking about the solution to a dynamic model is from the point of view of sequence space or something. We do not think of it that way when we solve, in this course, we are not going to think about solutions in that way as sequences. We're going to think about solutions as functions. This is this functional analysis approach to dynamic models. There are actually weird cases where you have to think in terms of sequences. We will not touch any of those cases. I don't believe Jesus will touch any of those cases in this course. So we will think about a solution as a time-invariant function g, as a function of kt, as a function of the variables, so to speak, kt, at, and I'm going to think of sigma as a variable, but it's not a time variable. It's just a constant variable. It indexes the problem, but I'm going to think of g as being a function of that variable. When I have sigma equal to 1, I'm dealing with the policy rule associated with the problem I'm actually interested in. When sigma is equal to 0, I'm dealing with the policy rule in a different problem, the one in which the epsilons have no uncertainty on them. Okay, so this is the function. I'm going to look for a solution. By the way, notice that this function delivers sequences. By just iterating on this function, you can fill out an event tree and put in the capital associated with every possible sequence of shocks into the future. So this certainly implies a sequence, but not all sequences can be represented as the solution to a time-invariant function like this. So if you write down an economic model where the solution is not a time-invariant function, sometimes you can't use these methods. I don't know if I'll get to this, but one classic example where you seem to get time-varying functions is with the Ramsey problem, and even those we can trick into this anyway. So, any event. Okay, so we're going to think of a solution as a time-invariant function g, which sets this guy equal to 0 for all possible values of the state. So the state is the things that are known at the time that this decision here is getting taken. There's only one random variable there's only one random variable in the whole picture here, which is from the point of view of this functional equation, there's only one random variable. This a here ain't no random variable because it's observed. The only randomness is in here. So what I'm going to try and do is find a function g that satisfies this. Now, we all know there's also a transversality condition here. And I'm going to look for a function g without even thinking about the transversality condition. Well, we'll think about it a little bit occasionally. We'll see that in a minute. We'll think about it a little bit. In practice, the way you check to see if the transversality condition is satisfied is you check to see if you get an ergodic set for the case, because you know then that the transversality condition has to be satisfied. Generally speaking, however, the word transversality never is used in these discussions. But I'm sure some of you are thinking, well, this is not a sufficient condition for an optimum. We also need a transversality condition. Where the heck is that? Well, it's floating somewhere in outer space. Okay, so let's first talk about the projection methods. So for the projection methods, I'm going to look in a space a parametric function for g, and that space I'm going to look in either the finite element space or in the spectral space, and then I'm going to have and I also have something to set to 0 here, which is I would like to get this function here to be 0 for all possible k and a. And so, but I can't do it for every conceivable k and a, because only the true function will do that, and the true function is infinite dimensional, and I'm only going to attack this thing with finite dimensional functions. So in general, I'm not going to set this to 0 everywhere. There are, of course, special cases where you can. If utility is log and if depreciation is 100%, then of course you can find that function. But that's an isolated case. It's actually of zero interest in the dynamic stochastic general equilibrium literature, which tends to be focused on monetary economics and stuff like that. And so that the 100% depreciation assumption in the special example where you can calculate that thing exactly, the 100% depreciation assumption you have to make makes that model totally uninteresting from a short-run analysis point of view. Maybe 100% depreciation must mean the model is like a 30-year model or a 40-year model or something like that. I'm not sure what. Okay, so that's my policy rule. So the projection methods, there's my approximating function. It's living in it's a finite dimensional function. And then what I have to do is I want to choose the parameters gamma to make this thing as close to 0 as possible. And then I can use galerkin or collocation. Now maybe by just sort of looking at that and pondering it, you can realize this is actually a humongous problem. Because let's take the extreme case where the A is a continuous variable. Then, let's start with the easy case, where A can only take on 5 values. So one way you can think about this is that you want to get you could think about if A takes on 5 values, you can imagine looking for a different policy function associated with each possible realization of A. So if A can take on 5 values, then your gamma of A would be 5 different sets of parameters, one for each value of A. The K, however, that's always going to be a continuous variable. There's no way to make that anything non-continuous. So now you're having to solve with this endogenous thing, you're having to solve for 5 policy functions if you suppose that A has only 5 possible realizations. Well, that's a big job. Oh, one thing I should add, this is a one capital model. Suppose we have some other things in the model. For example, suppose we have entrepreneurs who have net worth. Now you have a second state variable, and that has to go in there, and now I have doubled the size of the function that I have to go and find. What if it's an open what if it's a two-country model? Well, then I need at least 2 capital stocks. I mean, pretty soon it gets to be a nightmare to the power 4 to try to imagine using a projection method. But projection methods are quite tough. It's not a problem. It's not a conceptual problem. It's interestingly, in this age of fast computers, it's a huge computational problem that even with fast computers did not fast enough to do this in any normal person's lifetime in a serious sized model. By the way, we could mention right off the bat here that the projection methods will work in this case when you have what's called occasionally binding constraints. So the obvious kind of occasionally binding constraint in this type of model is non-negativity constraint on investment. That's investment over there, so you can have that constraint there, which would be, and that constraint's going to be binding for some k and non-binding for some k comma a, and non-binding for others, and that's why you could call it occasionally binding constraints. Maybe you can see right off the bat, I haven't written this out more carefully, but maybe you can see right off the bat that this fits right into the framework that we've been talking about, because what you do is you imagine writing up the RBC problem in Lagrangian form. So add this constraint as a Lagrangian constraint, so attach a multiplier to it, and then include that in the problem. And then you get one of the conditions, a complementary slackness condition. You get a condition that the multiplier times that thing has to always equal to 0, and the multiplier and that thing have to be greater than or equal to 0. Well, that just becomes, that thing equal to 0 becomes part of my error function. And the multiplier is another policy rule that I have to go and find. So it fits in quite nicely into this error function perspective, even if you have occasionally binding constraints. This paper with Fisher was completely devoted to occasionally defining constraints and goes into many, many different issues and stuff about that. But it should be maybe obvious that it doesn't really, even if you have inequality constraints that bind sometimes and not other times, you're still basically in the environment that I laid out even with my toy example. Okay, but let's talk about the perturbation approach, which I say is not feasible in the occasionally binding constraint case. Well, first of all, to apply this thing, at least to apply it kind of naturally or normally, you need to know the value of the function at a point. Well, that's no problem in the case of the new classical model because, and this is the miracle of that model, you can compute the steady state of that model without knowing what the policy rule is. Now, I always used to take that for granted. I never thought of that as a miracle. But actually, there are models out there, models of strategic interaction between agents, where this feature is it's not a feature. So if you have the government, for example, is choosing monetary policy and it's thinking about the reaction of the private economy, well, the reaction of the private economy is itself an equilibrium function object that has to be computed. And the government's behavior is going to involve, to some extent, differentiating that equilibrium object. So any concept of steady state in such a model of strategic interaction involves an Euler equation that has the derivative of the damned unknown function that you want. And so even in the steady state, the function is there and you can't get rid of it. But in the neoclassical model, you can calculate the steady state without knowing what the policy function is. In fact, all the models that I've seen being analyzed today have that property. The models in macro where there was a strategic interaction between the government and the private guys, and in I/O where you have strategic, the result first comes out in I/O models where you have strategic interaction between, whatever, duopolists or something like that. Those models don't seem to be used so much in macro these days. And so that limitation of this perturbation approach isn't so obvious. Now, by the way, I should add one thing, though, which is that Crucell and Victor Rios-Rull wrote a paper where they showed how to adapt the perturbation approach when the strategic considerations arise. However, it gave rise to a horrible fight. Ken Judd declared a fatwa on them, and they are now hiding. No, that's not true. But so there's a lot of controversy over what happens in when there's strategic interaction, because when there's a strategic interaction, there is no kind of point where you know the policy rule. There's the value of the policy rule. The only, in the strategic interaction case, all the points have the property that the value of that error function depends on the nature of the policy rule. Anyway, the overwhelming majority of models used in macro at this moment do have the property that you can compute a steady state for those models, and you don't need to know the policy rule to do that. All right, and that's the non-stochastic steady state. Now, the non-stochastic steady state is a special case of the model I wrote down, because that's the case where sigma is equal to 0. In the sigma equal to 0 case, that model is non-stochastic, it's deterministic, and in that case, I can find a k star that has the property that I know what the value of the function is at that k star, namely it's k star itself. That's I mean, all of you know that. But it turns out that's of critical importance for straightforward application of the perturbation approach. As I understand it, Ken Judd's working on the correct way of doing this now, but at least as of last night, he hadn't totally figured this out yet. Anyway, so what we do is to apply the perturbation approach in the neoclassical model, we've rigged the model, but there's one parameter in there, there's a sigma, so that there is a point in the state is now Ka and then sigma. There is a point in the state where I can evaluate, where I know what the G function is. I set there's a K star, I can find it, there it is, and where I set the A equal to 0 and the sigma equal to 0, and there it is. So I have a point where I can evaluate this function. The error function is this thing here. This is the thing we wrote down before, and for the true g function, this is 0 everywhere, no matter what sigma, no matter what k, no matter what a, as long as they're admissible, of course. And in particular, all the derivatives, because r of ka, because r is 0, no matter what k, a, and sigma is, the derivatives of r with respect to k, a, and sigma are 0. Now, we're assuming some differentiability here, of course, but anyway, they're all 0. There's going to be differentiability assumed inside these functions. What I want to do now is I want to show, I guess it's 4. I hope it's not 3, in fact. I want to show 4 properties using this simple neoclassical growth model. I'll show you 4 results that we learn by doing perturbations, and the 4 results are actually completely general. They're not of r with respect to k, a, and sigma are 0. Now, we're assuming some differentiability here, of course, but anyway, they're all 0. There's going to be differentiability assumed inside these functions. What I want to do now is I want to show, I guess it's 4. I hope it's not 3, in fact. I want to show 4 properties using this simple neoclassical growth model. I'll show you 4 results that we learn by doing perturbations, and the 4 results are actually completely general. They're not get the squiggle equals, so it's not exactly equal. And then I've got the first term there is the linear term. The variables in this argument are k, a, and sigma. There's the linear term. And then here you have the quadratic terms, and then the dot, dot, dot means the higher order terms. And I want to say something that we know about that's very easy to show, actually, using the neoclassical model that I've already described, and that is true also more generally. So number 1, the first observation is that to a first-order approximation, certain equivalence is true. That is to say, the first-order approximation of the policy function has the property that sigma don't make no difference. The coefficient on the slope term on sigma is 0. Trivial to show here, true generally. So certainty equivalence is the right way to go if you're doing a first-order approximation, first-order perturbation, I guess you could call it. The other interesting property, also completely general, is that all the coefficients in that Taylor series expansion except one, involve linear equations, are trivial to solve for. The one exception is G sub k, which involves looking at eigenvalues and which is complicated in some sense. We'll see in a second. It's a sense in which you already know, but we'll just get it all on the table at the same time. So the one parameter in there that's kind of complicated to compute, and it involves looking at eigenvalues and stuff. But conditional having solved for that, all the other ones are solvable by linear expressions. Another result is that to a second-order approximation, so bringing in the second-order terms in there, we find that to a second-order approximation, all slope terms are independent of variance. So G sub k sigma, G sub a sigma, which are the slope terms in here, are also 0. The way uncertainty starts to creep in as we go to these higher approximations is through this, you could call this intercept term. This guy here is going to be non-zero. Again, these are trivial to show in this example. And then, of course, if we go to third and fourth higher terms, you're not going to get any simple zeros out of that stuff there. But it's kind of interesting. To a first-order approximation, it's kind of fun that you can show so easily that these little results. And then the third thing is a recursiveness property, which I've already pointed out in the toy example, that you can compute the linear approximation without ever thinking about, they're not joint, you don't have to solve jointly for everything. You can go recursively. You solve the linear, and then in order to solve the quadratic, you need the linear as input, and then to get the cubic, you need the quadratic and the linear as input, and so on. You can go recursively and go as far as you want. You can, of course, see that the notation is going to get to be a nightmare very, very quickly. And as I say, the actual programming of these things is all about how to manage this complicated systems that you end up getting. This, by the way, has all been done now in DNAIR. DNAIR will do, I think, the kind of the plain vanilla DNAIR that you just pull down from the web, version 4.2.1, will do third-order approximations. And then, there's like a super-duper secret stealth weapon version of DNAIR that only certain people with the right password can get, will do any order approximation. Okay, so let me just show, I'm not totally going to show you this, but I'm going to get incredibly close to showing you the properties of the key property that about the first order approximation there is the G sub sigma equal to 0, and the other one is that the G sub k is a complicated thing. That's the key thing that we can show with the first order approximation. And the way you do that is you take the derivative of that error function with respect to it's only got 3 arguments, and of course that's 0, and then work out the derivative and evaluate it. So we're doing everything around this one point, the non-stochastic steady state. So evaluate it around that one point, and then what you get is, you get 3 equations. There are 3 derivatives there. You get these 3 equations. Of course, they have to be 0 at that point, because the thing is 0 everywhere. So it's 0 everywhere. It's got to be 0 at that one point, too. And what you can already see here at the bottom, I'm pointing at the wrong thing there first. You can see at the very bottom here that the G sub sigma shows up multiplying this square term, the square bracketed term. The square bracketed term in general is not going to be 0. If it were 0, then that equation would say nothing about G sub sigma. But in general, that square bracketed term is non-zero, so that equation requires that G sub sigma be 0. That's a very important result, that G sub sigma is 0. To a first order approximation, certain equivalence holds. And then the second thing is that when you work out these derivatives, especially if you go to higher order, kk, ka, all these different things, what you find is that you never see the number 2 showing up, but except here. In the linear place, the number 2 shows up. The G sub k turns out to be, shows up as a square, and so finding what G sub k is a problem. Of course, this applies in the matrix case as well, so that you would end up with that G sub k would be a matrix, and something like the square in there. So let's look more. Now I've written out this first term here, this first equation, by dividing and multiplying and doing a bunch of stuff. I've written out this first equation and you end up with what is probably for most of you a completely, or at least for me, I look at that equation. If I woke up in the middle of the night, I would look at that equation and say, I feel so good now. That's the kind of the standard second order polynomial that you look at when you look at the Euler equation associated with a neoclassical growth model. If you want to have a hidden file, I think you have the hidden file, right? There's this nightmare of algebra associated with this thing where I explain how to go from that previous. I think you have that in the handout. Maybe you don't. Yeah, okay. So in any event, one thing I want to draw your attention to here, this is a big K, big K, big K. These are big Ks here. So these are derivatives with respect to big K. Only if this is a big K will you recognize this. If it's little k, it's not the same thing as you've always looked at. This is, of course, the curvature of the production function. This is the curvature of the utility function. Both of these are concave functions, so this, therefore, is a positive number. And the fact that this is a positive number and that this is 1 over beta implies that, well, we know there are 2 solutions to that thing, but it implies something about those 2 solutions, which is that there's one G sub k that's bigger than 1 over beta and one G sub k that's less than 1 that solves that equation. And so this is the confusing equation, because you got to make a choice which one to pick. And it's very straightforward to show that analytically. I mean, you just need a little diagram to show that. Now, in this particular example, the neoclassical growth model, you can show, theory tells you that you're an idiot unless you pick G sub k less than 1. The reason is that you can show theoretically that the policy rule cuts the 45-degree line from above. So you know that the actual thing you're trying to approximate is less than 1, and that this thing is something else. Presumably it has some interpretation. I have no idea what it is. But this other thing here is not of any interest. We know that in the case of this particular model. Now, in practice, of course, it doesn't always work out this way, and there's a lot of hand-wringing associated with this problem, this equation that power 2 is a problem because it gives rise to a decision which is the right solution. For example, you can find interesting models where there are two G sub k's that are less than 1 that satisfy that equation. And then of course in cases like that, you actually have multiple solutions. Those are examples where you have multiple equilibria. And well, they actually might be very interesting. I mean, they have the classic examples of strategic complementarities. I'm going to work hard if I know you're going to work. We're at a factory. You're making the wheels. I'm making. You're making the wheels on the car, and I'm making, I don't know what, the bumpers on the car. But I know that if your wheels suck, then what's the point of making nice bumpers? And I guess you don't have any reason to think that way of me. You think, okay, I make the motor, you make the wheels. So you make the wheels, you know that if I'm going to make a bad motor, you have no reason to make decent wheels. If I think you're going to make bad wheels, then I have no reason to make a bad motor. So these are strategic complementarities. We have an equilibrium here where we could just both make crappy stuff. On the other hand, if both of us think the other one is working hard, in this example, you have another possible equilibrium. So one of the standard sources of multiplicity in dynamic models is these strategic complementarities, where the return to my effort is an increasing function of how hard I think you're working. It's not the only source. We'll talk about another one when we get to the Dynera example, but these kind of things do happen, and then you really have to struggle. Now, there are also examples where both G sub k are bigger than 1 in absolute value. Now, if it's bigger than 1 in absolute value, well, I'll tell you this, 99.99% probability is that you made a mistake. There are economic models where both the G's are bigger than 1 in absolute value. But yeah, bigger than 1 in absolute. In fact, Stokey and Lucas have a nice example in their chapter 6. But it's a goofy model, crazy model. I've never seen a real model that had them both bigger than 1 in absolute value. So that is a possibility, though extraordinarily unlikely to be actually a true possibility. That is the thing that could occur. Of course, in the case where they're both explosive and you haven't made a typo, all these methods are irrelevant, these computational methods. Because the computational methods assume you're going to stay in a neighborhood of the point where you're doing the perturbation, and if you're going to wander away from that neighborhood, you have no justification for using perturbation methods, because perturbation methods are only going to be valid in a neighborhood. So if you find that they're both bigger than 1, you better hope you made a mistake and that you find that mistake, because if your model implies bigger than 1, then you can't do perturbations. Okay. Now, once in this particular example, once you've figured out which G sub k you're going to use, then G sub a is simply found by a linear equation off of this guy here. If you look inside here, you'll see that G sub a appears everywhere linearly. This E sub g is showing up because e to the power g is there because it's the exponential of g that appears in the return function. Okay. All these results completely generalize to finite dimensions. So it is always true that when you do these perturbations, you're going to have a G sub k problem. In practice, that problem is not finding the eigenvalue of a polynomial. It's going to be finding an eigenmatrix of a matrix polynomial instead, but it's still the same thing. And the analog of G sub a, which is the feedback onto the exogenous variables, is always a simple linear function of whatever you did with a G. It's finding G sub A is always involves solving a simple linear equation once you figure out what G sub K is. Let's go to a numerical example to try to pin down stuff and see as an illustration here of things. So what I did was I took the neoclassical growth model. Now this doesn't, Prescott in 1986 wrote this paper about the real business cycle models. In that model, he has hours worked in there. Of course, we don't have hours worked here, but I tried to pick parameters that looked like the one that he picked. He actually used log utility, but I wanted to make things tough. So I used gamma equal to 2. Gamma is the risk aversion. Also 20. We'll do gamma 2 and then in parentheses 20. This is the share of income. This is going to capital. This is depreciation rate. This is supposed to be a quarterly model, so it's 2% per quarter, 8% per year. The correlation parameter that he said was correct is 0.95. And then the variance of the shock, of the innovation to the shock, he estimated was actually 0.75%. I got 1% in here, so I'm making it a little bit on the big side. And then I went off and computed the second order approximation. So this g hat function, here's the g hat function. It's a function of k star. This is the logs again, so this is log of k star. I don't know what that means exactly. And then you have the slope coefficient. The slope coefficient is 0.98 with this risk aversion, and it's much bigger with that risk aversion. This makes perfect sense, by the way. See, when g sub k is big, it means that for a given, because this is now all in terms of the log of the capital stock, this is now the percent deviation from the steady state. So what g sub k is, so k minus k star is a gap between the capital stock and the steady state, and g sub k controls what happens to that gap in the next period. If g sub k is very close to 1, then the gap is being narrowed very slowly, because the gap this period is about the same as the gap last period. If g sub k was like 0, then whatever the gap was last period, you'd had the gap closed in the current period. So what's happening when gamma is big is that the gap gets closed more slowly. The g sub k goes up. This is a standard kind of result for good reasons, which is in order to close the gap and go to steady state, you got to not eat so much right now. And that's a painful thing if your gamma is really big, because there's a lot of curvature in that utility function, and the less food you have, the more unpleasant it is for you in that case. And so you get slower convergence when gamma is equal to 20. There's no surprise there. This is the coefficient on the realized value of the exogenous uncertainty. That's g sub a. That's equal to this number here. Here we have the g sub sigma. This is not 0.000. This is 0. Completely 0 here, times this sigma. So if I made the sigma equal to 0 or 1, it makes no difference to the linear approximation. This is the certain equivalence thing. Now we get to these other terms here, and then what we get, these second order terms are really rather small. So for example, here's g sigma sigma is 0.00024 times this number here, but this is a number between 0 and 1, so this is times, but then you have to square it. So this adjustment, and then you have to divide it by 2. That's not a big deal. So this term here plays a very, very minuscule role. If you look at this term here, here's another quadratic term. It plays a very small role. Like, for example, suppose that you're 1% below the steady state. In normal fluctuations in the United States, you're going to be 1%, 2%, something like that. Well, 1% is 0.01. So this number will be 0.01. Now you square it, and it's 0.00, whatever. It's a whole bunch of stuff. And then you multiply it by that, pretty soon you got the thing is squished down and not doing very much. So looking at, here's the slope terms I was describing before. These are exactly 0. Notice as you go to second order, see, this is a linear, it's a quadratic term in terms of the sigma, but sigmas are constant. So you can think of this as actually linear. So if you go back to the linear representation, you could just sort of think of this as being part of that, not in the Taylor series expansion sense, but in the real sense. And so what the fact that this is 0 means is that see, this term here looks like that. This should be a star. This term looks like that one. So the fact that this is 0 is saying that uncertainty also does not affect your reaction to this thing here. It does not affect the constant term, but it also doesn't influence your reactions to things. Gee, this guy here is 0. Your slope doesn't respond. It's just total certainty equivalence here. Both the level and the reactions to things in the linear representation are 0. This is the kind of the basis for thinking that with normal fluctuations, with normal preferences, and studying just aggregate variables like consumption and whatever, that the linear approximations probably give you decent stuff. Now, at the same time, we know we don't do terribly well on financial variables, so we may want to look at more interesting utility functions and so on. Then the second-order approximations might make a difference, even in a country like the United States, where you have not very volatile data. If you leave the not very volatile post-war United States, say, and go to the Great Depression, then the linear stuff is no good, and you need nonlinear stuff. If you go to Argentina, you're going to need the nonlinear stuff and so on. If you go to Europe, fine. Just post-war, it's fine. I don't know where this Greek thing is going to take us, but for the time being, post-war Europe is fine in terms of linear approximations and not getting into any super exotic preferences and stuff like that. So the conclusion from this example here is that for modest US-sized fluctuations and for aggregate quantities, it's probably reasonable to work with first-order approximations. What is the first-order perturbation? Take the equations whose expectation we're trying to set to 0, replace them by linear equations, and then solve the resulting system. Do the linearization around non-stochastic steady state, so we're implicitly supposing certain equivalence, and this is okay as a first-order approximation. Let me give you the general sort of description of linearization. That's the last slide in this discussion here. The general thing is here you have these dynamical equations here so think about these are the Euler equations, but also, resource constraint and all the equations that characterize the equilibrium are all lumped into here. And they involve two types of variables. One type of variable is this vector S, which is the exogenous variables, either the shocks. And another type of variable is this vector Z, which is the ZT contains all the endogenous variables whose values are determined at time t. So this is a pretty canonical, in fact, it's completely general in some sense, because any system, even if it involves equations that look really far into the future, can always be written in this kind of first-order form. Anyway, so there's a canonical representation of a set of equilibrium conditions, but written after expressing it in linear form after taking the linear Taylor series expansion around steady state. The system is then completed when I write down what the law of motion is for the exogenous shock. So there it is. And okay, so then the way I solve that thing is I'm just going to posit a linear solution, A and B, and so this is the analog of G sub k here. This is G sub k. This is G sub a, and ST here is the analog of A. A, of course, was a scalar. Now this S can be any vector whatsoever of any length. And the way we solve these things, for A and B are unknown, we use the method of undetermined coefficients. Method of undetermined coefficients is a solution method that pins things down by what they're supposed to do. Okay, what A and B are supposed to do is they're supposed to, when you plug in Z according to this law of motion in here, it's supposed to set this thing exactly equal to 0 for all possible values of ZT minus 1 and ST. Those are the state. So to do that, it's a totally straightforward algebra. Stick this thing in here and deduce the implications for the requirement on A and B that this has to be 0. What you find is that the matrix A has to satisfy the same type of polynomial equation that G sub k did before, except now it's generalized because these are matrices now. And then, conditional on what you find for A, the solution to B is completely linear. This is this thing having to be equal to 0 is linear in B, conditional on the matrix A. So you got yourself. The thing on the right is no problem. The thing on the left, problem, because that's a matrix. You know, we know that with scalar polynomials, there are multiple solutions. Well, you can bet your life that with matrix polynomials, there's even more solutions. So solution algorithms that go to work on this thing, what they do is they look at this equation and they ask themselves, what are all the possible A's that solve that equation? Now, it turns out it's completely trivial to instantly figure that out. Instantly figure out and put them on the wall. It's a finite number, so you can put them all on the wall, like Linearization does this. It puts them all up on the wall like that, all the possible A's that solve that equation. Then it calculates the eigenvalues associated with each one of the A's, and then it looks, and if it finds only one that has all the eigenvalues less than 1 in absolute value, then it says, aha, that's the A that I want. If it finds 2 that have eigenvalues that are less than 1 in absolute value, it crashes and sends you an insulting message that Blanchard-Kahn condition is not satisfied. I'm not sure that should be insulting, but you feel bad when you see the message. And another possibility, of course, is that when it looks through all the A's, it finds no A that has eigenvalues all less than 1. Then it crashes also, and because that doesn't. So it's going to look for a unique A that solves that thing, and if it does not find a unique A that solves that thing, it will then crash. Obviously, if there are 2 A's that solve it, then there are really 2 equilibrium. The 2 equilibria. You asked it for an equilibrium, it found 2. So then it crashes because it doesn't know which one to give you. Now, there's all kinds of interesting things that happen when there are 2 A's. First of all, you have 2 equilibria, but you also have a continuum of sunspot equilibria attached to it as well. You could imagine actually modifying Linearization so they will give you all menu of possibilities when you have multiple A's, but that's not the way it is set up right now. So if you have exactly one that has eigenvalues less than 1 in absolute value, that's the solution, and otherwise you have many solutions. And conditional on the matrix A, you then solve a simple linear system, which is that thing up there, to find B.